All right, part 3. But before we get started with anything, I have to address something that an egregious error that was made in the last video. That I have to just start with this because it was the top comment, and that is that I used the wrong peak. It's supposed to be P-E-E-K, not P-E-A-K. Look, I'm a programmer, not an English major. What are you gonna do about it? But I did like to joke about this being peak content, so that's pretty good. All right, you know what? We can do a find and replace. All right, we're gonna replace peak with peak. All right, we'll do replace all and look for anywhere else. It was used in another file. It's all over the place. All right, does that cover all of it? All right, and because this was such a bad error, I've basically been canceled for this. And I don't know if you guys can even trust me again. We are going to make it its own commit, and we're going to name the commit message "Repair My Reputation." All right, and hopefully that will do it. And now we can actually continue with the regularly scheduled programming. So today we are doing variables. So what we're doing, if you don't know what we're doing, we're making a compiler with our own programming language called Hydrogen. And so far, we have the ability to just output an exit code. So if we were to compile our language, which we do just by running it here, we will get an out file in the CMake folder where the executable is. And if we go ahead and run it, and then we go ahead and echo $? To get the exit code of our executable, we get 100, which is what our programming language specified. And so we're compiling to assembly and then using NASM to convert that assembly into machine code, and then using the GNU linker to link it into a final executable. And if you want to see what the assembly looks like, it does actually output the assembly, and here it is. So it turns this exit 100 into this assembly. Pretty basic. This is all we can do so far. So let's extend the language. Let's do something interesting. So let's think about how we want to do variables for the syntax for variables. So let's do let. Okay, because that is the trendy keyword to declare variables today, right? We're not doing var, okay? Because honestly, var versus, let x equals 7, var x equals 7, like it's harsher sounding, all right? It's not cool, and the most important thing when you're creating your own programming language are the aesthetics of it, and we want this to be a pretty language, as well as being the most safe language. So we're gonna do let x equals, let's just do 7, and then we can do exit x. And you know what? Let's actually finally add parentheses around our exit because we wanted to make it look more like a function, even though we're just treating it as a built-in for now. So I think we'll go with this, right? We'll do this. So, okay, what should the next step be? The next step should be looking at our grammar for our programming language, and modifying that one first. And we're gonna have to do some things to fix this up to get what we want. So first of all, right now we have just this exit as our kind of entry, our entry production, initial production here, root node, I guess. But that doesn't really make much sense. Let's actually create a program. I think that would make more sense, like a program node. Okay, so let's go ahead and do, I don't know what this formatting is that just happened here. Okay, whatever. So we will do, we'll do prog for program, and we don't want it in italics. And let's give this 2. And for our program, it's going to be a list of statements. So we'll have a statement node, and then we'll just allow any number of them. I guess including 0. I guess you can have a program that just has no statements. We'll just say that's valid. Why not? So we'll do, for right now, not sure if this will stay in the future because of the way we might architect this compiler or construct our AST and stuff. But we will do a statement, and then we will do a star. up here, meaning that we can have 0 or more of them. If you do a plus, that's 1 or more. That's just kind of the convention for writing grammars. So we have that, and now we need to define what a statement is. So a statement is going to be, wow, I don't know what this formatting is. This is terrible. I really don't know what's going on here. It's strange. Maybe I can do a bit of that. We'll clean it up later. So a statement is actually going to be one of two things. It can either be our variable declaration, or it can be our exit. So we're gonna have to do something a bit different here. And I think in order to kind of lay this out in LaTeX, we can do something like begin cases and then end cases, which should give us this like bracket here, and then we can put multiple different productions in here. So we can have an exit, and I think I'm just gonna just like inline the exit here, and we'll get rid of the exit production because I don't think we really need it there. So we'll have exit like that. Okay, and then we will also have the variable declaration, which will be let, and then we'll have an identifier, and we won't do this in italics to specify this is this is some type of token, and then an equals, and then it'll be equal to some sort of expression. So we will do text expression, and I just realized this should be in brackets up here. Okay, and then we need our semicolon, just like that. So a statement can either be this exit with parentheses, and then the expression is right now is just an integer literal, and then we can get rid of this exit here on its own production. We don't need it anymore, so we'll get rid of that. Okay, and I think that pretty much does it. So this should be enough of a grammar to express the syntax changes we've made. So let's go ahead and implement that. So we're going to have to make some changes. Oh, you know what? Before we even do that, there is another mistake that I made in the last video, a bit of a more serious mistake. I think someone picked up on it, but if I go to my tokenizer, I actually have to, if inside of peak, the newly spelled peak, I'm not actually using a head here in this return here. This should be plus a head. That's a mistake. And I think also what I want to do is I'm going to start this at 0. And the reason why is because in order to peak the first character, we're starting at index 0, and we need to peak the first character. So peak should not look at the next character by default. It should look at the current character, and then optionally look further ahead. So I think instead of ahead, maybe we name it offset. So it's kind of a bit of an off by 1 error here, just things like that. And I think that'll do it. And then we pretty much copy this in our parser because this also has its own peak. So let's actually fix this one as well. So let's make this offset and then plus offset. And warning is redundant. What is the problem? Oh, greater than or equal to. Wow, C-line actually actually caught that. That's pretty cool. This is why you use IDEs that use 10 gigs of your RAM. So you don't need Rust when you have your IDE to do all the checking for you. Okay, so let's actually make sure that still works. So let's just go back to what we had before to make sure we didn't break anything. So if I run it, we get you messed up. Okay, so something's wrong somewhere. So that bug fix broke something, which is unfortunate. So what exactly is the problem? So we start off at 0. Okay. So let's debug it to figure out exactly what happened. Okay, we need to set a breakpoint on you messed up, wherever that's... we need to clean up these error messages as well. Let's see if it's this one. Okay, so it is this one. So what is the problem? X. Ah, did I not save this file? Maybe I... Oh, X, you can't do that. You need to put in a number. Okay. Cool. Okay, so that actually fixed it now. So now our peek and consume should work correctly. Let's just verify it one more time. 10. Okay, that's cool. So now let's actually make the changes. So let's start out with just adding parentheses. So let's take this step by step. So let's add parentheses to our exit. So in our tokenizer, what we actually have to do is introduce a couple more tokens. We need to do open paren and close paren for the parentheses. And then we need to actually check for it in our tokenize for our file. So we're checking for a semicolon here. So maybe before that we'll do else if peek.value equals open paren, then we will go ahead and consume that token. And then we will do tokens.pushback, and we will give it the type of token type open paren. All right. And then we will do the same thing for the close paren. Okay. Don't know what's going on. Okay. Just like that. Boy, I'm making all kinds of typing mistakes today. Oh my goodness. Sea Lion, I just complimented you. Stop messing stuff up. Okay. Type equals token type close paren. Okay. Cool. So now that should actually give us our tokens. And so now when we go to our parser, if we were to run it now, I don't quite know what's going to happen. Invalid expression. Okay, that makes sense. So it's trying to, yeah, so it's trying to parse expression with the parentheses in it, but the parentheses need to be part of the exit. So when we go to our parser, under parse, this should actually be called parse exit. We'll clean that up. And what we're going to do here is, so we're peeking if we have an exit, but we also need to peek if the token after that is an open parenthesis. Okay, so what we need to do is and peek with an offset of 1. See, I'm mistyping it now. I'm so used to it. Peek.value. Well, we need to make sure it has a value at all, if there even is another token. So if it has a value, and peek1.value and the token type equals token type open paren, now we can actually consume both of the tokens. So we consume the exit, we consume the open parenthesis, we then parse the expression, and then after we parse the expression, we need to consume the close parenthesis. Okay. Actually, I don't know why I put invalid expression here. This should be expected expected semicolon. And so before the semicolon, we need to check if peek if peek.has value and peek.value.type equals token type close paren, then we consume the closing parenthesis, else we can give it an error message saying that we expected a close parenthesis. Okay, so now if we run this, I think it should actually work. And 10, okay, cool. But let's intentionally make a mistake. Let's forget to close our parenthesis, and we should get a decent error message for that. Oh yeah, look at that. Expected close parenthesis. We don't have a line number or column number. We'll get to that at some point. Or if we forget, I don't know, if we do exit, I don't know. Is that gonna work? Ooh, we get an infinite loop if we do this. Maybe I should debug that. I wonder why. So we have an exit. Where is it actually going into the infinite loop? So we're at peak, but where are we? We're in parse. Oh, you know what? This was a mistake too. I don't know why I have a while loop in here. So this should be renamed to parse exit. You know what? We're gonna refactor all this anyway, so let's not even deal with that. Okay, so this will be fixed anyway because we're gonna clean up the parser. So let's actually do our expression. So let x equals 7, and then let's put an x in here. Okay. Oh, and you know what? There is actually one other thing we need to do with our grammar, because right now we can do exit with an expression, but an expression can only be an integer literal. So that means that we can't have an identifier in here. So an expression needs to be two different things as well. So we're going to do begin cases, end cases. We're going to throw in our integer literal in there, but then we're also going to put in an identifier, ident. And we need to put in a new line here. So an expression can be an integer literal or an identifier. And then obviously we need to check if it's a valid identifier, but that'll be during, at some point, maybe code generation. Not sure yet. Okay, so we have let x equals 7. Okay, so let's figure out our AST nodes. So right now we have node expression, and I think what we want to do for node expression, so we could have a token for an integer literal, or it can be an identifier. So we need a way of determining which one is which. And I think we could use like an enum or something. I think I want to use a variant, because as we add things to this, we're going to have more and more different combinations of things. And I think I'll use a variant, which is essentially a tagged union, which means I need types for them. So let's see if this works. So we'll do node expression, int literal, and then we'll do node expression identifier, and we'll have the token for the int literal, and then we'll have the token for the identifier, and then in our node expression we'll have a variant. So we need to include variant. Let's include it above here, include variant, and then we will have it be node expression int literal or a node expression identifier. And we'll like call it var or something for a variant, meaning that it could be either one. So what a variant is it's essentially a tagged union, which means it picks which one has the bit. It means that the type can be one of any of the specified types in this that are declared here. And the way that it works under the hood is that it finds the type that has the biggest size. Right now these are both the same size, but if one was bigger than the rest, it would allocate that amount of space. And so then it could fit any type in there. Obviously a smaller type would then have wasted space, but I mean, as long as the types aren't that big, it's not a big deal. But the great thing with the variant is that it keeps a little bit of space to keep track of which type you actually assign to it. So it knows what type it is. So during runtime, you can actually check and say, hey, what type are you? And then you know for sure which type it is. Versus a normal C union, you don't know which one is which unless you specifically add some sort of variable to keep track of it yourself. But variant is a container that has that keeps track of what type it is. So it's a union type. Okay, so we'll do that, and then we won't have a node exit anymore because we want a program. So let's have a program. So node program, and then the program will have a list of statements. So we'll just use a vector for now, and this will be node statement, and we'll just do like statements. just like that. And we need to go ahead and create our node statement, which also will need to be a variant because it could be multiple things. So we'll do a variant, and it will be node statement exit or node statement let for variable declaration. We'll call it var, and then we will create these node statement exit. It's a struct, and for our exit, really the only thing we care about is the expression. So we'll have an expression in here. So node expression, and this will be the expression. And then for our node statement let, we actually care about two things in here. We care about the identifier and then the expression. So we'll have, so actually our token is going to be our identifier, and then we need the expression. So node expression for our expression. Okay, so that'll do it. Never used. Okay, I know. That should be good. Okay, so oh, and someone asked, why am I prefixing it with node instead of doing like why node exit instead of exit node? Because, you know, in normal English you would say exit node, because for IntelliSense mostly, because it's better to start off if all of these different types have something in common, which they do, they're all a node, then I want to put the common thing first. So that way if I use it somewhere, like over here, I can type in node, and look, it auto fills it with all the different nodes I have. Versus if I put the node at the end, then, I mean, it might show me it at the end, but this is way more reliable. This just makes more sense to put the common thing at the beginning. I do this for variable names as well, not just types. If anything that's in common between things, I'll try and put them first. Okay, so now we have a bunch of problems here because we changed a bunch of stuff. So we have parse expression. Okay, so let's go ahead and fix parse expression. So our expression can either be an integer, literal, or an identifier. So what we need to do is, so if peak has value and peak value is integer literal, we need to construct the node expression, but we actually need to create a node expression. Let's see. We need to set var to a node expression int literal, where the int literal is the token we consume. Like that. And if that is unsuccessful, we don't just return null, because it might be an identifier. So then we can check if it's an identifier. So else if peak.hasValue and peak.value.type equals token type, and I don't think we actually have an identifier type yet. No, we don't. So let's actually just stop here and go in here, and we'll include an ident. And over here, so this is where we check for keywords. So if it's not a keyword, then instead of erroring out, we then create an identifier from it. So we'll do tokens.pushback and make it a type, token type identifier, and it'll have a value. So dot value equals everything that's in our buffer. Okay, and then we'll clear our buffer, and we can continue. Actually, so maybe I can put a continue. I'm not sure if I need the continues. I'll look at it later. But okay, so there we go. So now in our parser, we can do is, so if the expression, we're parsing an expression, we have a value, and the type is a token type of identifier, then we return a node expression where the expression is a node expression with an identifier, where the identifier is the token. and we need to put in a semicolon. Okay. Cool. Now, now we need to do, we have parse. So let's do our parse statement. And this will kind of work in a similar way to our parse expression because they're the two different options. So we'll return an optional because if we fail to parse it, we just return null. Instead of creating a result type, we're using optional for that. So we're going to parse the statement, parse statement, and pretty much the same thing, just peak has value, and peak.value.type equals, and what are we doing first? Exit. So if it equals token type exit, and we want it to be an open parenthesis. Actually, so this is pretty much the same as over here. So we can actually just straight up copy and paste this. We don't need to reinvent this. So we'll copy and paste that there. Okay, so exit node, what is the problem here? Undeclared ident. Okay. Okay, so we need to actually go ahead and create node node statement exit, and we'll call it statement exit, and we need to give it the expression, which is node expression. Actually, it's what we return here. So we give it this. Yes. We actually need to set that equal. Value is never used. Okay, and then if we reach the bottom here, then we can return statement exit. No, because we need to make it a statement. So we actually have to do node statement and then set var and then statement exit. Like that. There we go. Okay, so that takes care of the exit. Now we need to take care of the variable declaration. So we need to add a let token. So actually in this case, let will be a token. Actually, exit's a token too. So I don't know why I have them in italics. Everything should just be text here. Really? If it's a token, I don't want it to be in italics. Okay, so we need a token for let, and we need to check for that. So else if buff equals let tokens dot pushback type token type let buff dot clear continue. Okay. And then we actually also need an equal sign. So we are just flying through creating new tokens. So we'll do equals, we'll just do EQ. And this will be a nice and simple one. We can actually just straight up copy and paste one of these. Equals, consume, semi, this is semi, it'll be equals. Okay. I think that's all the tokens we need. Yeah, so that'll be it. So under our parser now, where were we? Okay, so else, so if it's not an exit, else if peak dot has value and peak dot value dot type equals token type let, so let, and then we also need to check that the one after that is an identifier, and then the one after that is an equal sign. So we're gonna have to do a little bit of copy and pasting of this. So peak1 has value, and peak1 type equals identifier, and then we'll paste it one more time, peak2 has value, and then the type is equals. So if all those are true, so essentially we're just checking that these three tokens, that we have these three tokens in a row. Let ident equals. And then we can't check the expression yet because we need to actually parse that one separately with a different function. So we're in here. And so now we can start to construct our the AST node. So first we can consume the let, and we don't need that, so we'll just consume it, don't do anything with it. But the second one is the identifier, and we do want that. So let's actually construct our statement let is a node. Actually, let's just node, how do I want to do this? Node statement let equals node statement let, and then the identifier will be the next token we consume. And then the one after that is the equals. We don't need that anymore. So we'll just consume that, and then we have the expression. And so we need to actually parse that. Now, so we'll do the same thing before. So if auto expression equals parse expression. So if the expression is parsed correctly, then we will make statement let dot expression equals expression dot value. Else, we were not able to parse an expression correctly, so that means that there's some kind of invalid expression. So then we can actually print out an error here, invalid expression, and line, and then we'll just exit with exit failure. All right, and now we need to check if we have a semicolon. So then we'll say if peak.hasValue and peak.value.type equals token type semi. Then we are good, we can consume. Else, we need another error saying that we expected a semicolon. And after that, we should be able to, that means we've successfully parsed all of that, and so now we can return the statement. So we can return a node statement where the var is equal to statement let. Okay, and if none of these are true, we need to just return null. Oops, I can't just do that. I need to do return null. Okay, so those two are covered, and so now we just need to do parse program. So we will get rid of this parse, and we'll just do optional node program, and we'll do parse program. And what we have to do here, and because we have a list, we're going to have to keep going until we can't parse anything else. So we'll need a while loop. So while peak.hasValue, we will try and parse statements. So let's construct the statement at the start, and we'll do statement, and we'll make not statement, node program. So we'll do program, and let's see, program dot, and then we have statements. I believe that should just initialize correctly if we just don't do anything, I hope. Okay, so while peak has value, then we will continue to say if, we need to make sure that the statement's actually parsed correctly. So if auto statement equals parse statement. Else, if it's not parsed correctly, we will go ahead and do invalid statement and exit. Otherwise, we will do program.statements.pushback the statement.value. And then we should have a list of statements. And I think that should do it. I think that should actually do it. So now when we go to our code generator, we actually need to change some things. So we need to get our root. So instead of doing a root, we'll take in a program. We'll take in the program, and let's call this m program. Node program, m program, and program. Okay, so now our generator was pretty simple before, but now things are going to get a little bit more complicated because now we actually have to deal with the assembly and how do we actually store potentially an unlimited number of variables, because we can just keep giving them different names. I mean, the thing is we only have a limited number of registers, but you can declare pretty much as many variables as you want. I'm sure there's some kind of limit somewhere, but there's a lot more variables in registers. So that means we're actually going to have to utilize the stack. And we haven't done that yet. So let's see how we would actually do that. So first, what I want to do, instead of having just a generate, I want to have a generate for each AST node. Just like how we parse each AST node, we will generate each AST node as we traverse the parse tree. So what we're going to do is we will do, so we have generate. And so I think I'll call this gen program. Yeah, we'll do gen program, and we will, so the program will just start off with this start here, and you know what, if there is no exit, if they don't specify an exit, we will just exit with 0, and that's like how normal C or C++ works anyway. So in the code generation, we will just put in a 0 here. And I noticed I'm missing a new line here too. And then we'll put that at the bottom after we parse everything else. So if you do have an explicit exit, of course it'll just exit first before it gets to this point. So now this is where we're going to have to parse all of our statements. So what we'll do is we'll have a parse statement. Or no, not parse, generate statement. And this will be const. And we will go ahead and make this node discard. Okay, so we have a list of statements, so that means we need to go through them one by one. So we'll have to do m program. We'll do for const node statement. We'll take a const reference to our m program dot statements. So we're going to iterate through each of them, and then we'll do a gen statement. And in our gen statement, we need to take in a node statement. We'll take in a const reference, node statement, so we don't have any copying going around. So we take in statement, and then we'll pass in statement here. Just like that, and then we will do output. Whatever we return, we will put it into the output. So we need some kind of assembly that represents each statement. So first of all, we have to determine which statement we have, because if we remember, a statement is a variant, well, it contains a variant that can be multiple things. So what we could do, we could check each one individually with like if statements, or we could try and use a visitor. I don't know if I quite remember how a visitor works. Well, I know how it works, but I can't remember the syntax of how to create one. If you don't know what a visitor is, it's pretty much because we don't have we can't match on the type. So we have to have some sort of object that has an overloaded parentheses operator, like to call things. And then it will call the correct method depending on which type it is. So maybe I'll try this, because statement visitor, because I can't quite remember. Obviously this is a bit overkill for just 2 different options, but maybe in the future this will be useful. So I believe we have to overload an operator. So it'll be void operator parentheses, and then we do each type it could be. So it could be an exit. So we'll do a const, and we'll do statement exit here, like that. And then we have another one that is the other type, like this. So this is kind of like our match statement, our scuffed match statement for C++. And then now we need to visit it. So we would do statement, so we need to construct the statement visitor. So we do statement visitor, and then we do statement dot var dot, or no, we need to do visitor dot, never mind, I think it's std visit. Standard visit, we give it the visitor, and then we give it the var. There we go. All right, so we pass in the visitor and then the variant, and then now if it's an exit, it will call anything in this block, and if it's an I need to rename this. So if it's an exit, it's going to call anything in here. If it's a let, it'll call anything in here. So I mean, that's relatively clean for C++, I guess. Maybe difficult to understand. So, you know what? But we need to return something from this too. Oh no. So this is actually maybe even more complicated than I thought. Huh. Let's see. Let's just see. So if it's an exit, we pretty much just do this. So we'll do this, and then instead of, we do statement exit dot expression dot, oh, and our expression could be two different things as well. Ooh, so let's put a to do here. So we need a generator. We need to generate our expression. So we'll get to that later. Because we need to get to our expression. So let's have a string gen expression node expression, and this could be one of two things as well. So let's make a visitor for this. So we'll do expression visitor void operator, and our expression could be an integer literal. So we'll do that, and then int lit. We'll do expression int lit, and then it could also be an identifier. So we'll do void operator const this, and then this will be expression identifier. Then we will construct it expression visitor, and then we will do a visitor expression dot var. Okay. I think what we might need to do is, let's think here. If we have an integer literal, let's just pass it. Maybe, I think at this point we're going to have to push everything onto the stack. So anytime we come across an expression, we'll push the value onto the stack, and then whenever something needs to use the value of the expression, maybe it'll pop it off the stack. So in order to push something onto the stack, let's actually do a bit of Googling here. So x86 64 assembly push onto the stack. Okay. Whoa, I just got flashbanged. So we can push and pop. So okay, so you specify the register. If you don't know what a stack is, let's open up a bit of draw.io. Flashbanged again. Oh, this is what I had from last time. So a stack is a data structure where you can essentially stack things up. So these are like individual variables. So let's say we have 2, 4, and 69, of course. And so what we do is we have these variables, and this is our stack. And so we start by pushing things onto the stack. But as soon as we push something on the stack, we can only pop things off of the top of the stack. We can no longer remove the 2. Okay? In order to remove the 2, we have to remove the 4, remove the 2, and then maybe push the 4 back on. So order matters here. and then we can push things on. However, at least with assembly here, because assembly is not that safe, but actually in our favor, this is a good thing, is that we can still read from and modify the values in lower parts of the stack. We just can't remove it. So we can go into the stack and say, okay, I want 3 elements down into the stack, and I want to change the value to a 3. We can do that. We can set it to 0. We can do whatever we want, but we cannot just take it out. All right, this isn't like some kind of Jenga here. Okay, we have to do something like that if we wanted to remove it. So that's essentially what a stack is. So we can push things onto there and we can pop it off. But when we push to it, we need to push it from somewhere. And right now we have registers. So when we specify push, we push it from, like if this was the A register, we push from the A register onto the stack. And if we want to pop from it, we need to specify which register we want it to go to. So we might pop it into racks or RDI, and then it will pop it into that register. And there is a specific register that actually keeps track of where the top of the stack is, and that's called stack pointer. And that will automatically increment and decrement as you push and pop things on and off the stack. So that's a nice little convenience thing. You don't have to keep track of that yourself. The CPU will do it for you. All right, so we need to actually utilize that. So what I want to do is, if we have an integer literal, I want to push the value of the integer literal onto the stack, and then whenever we kind of bubble up from this generate expression and generate statement, whenever we need to use the actual value of that from that expression, we can then pop it off the stack and then put it in the register we want it to go in. So in this case, if we're using exit, we're going to pop it off the stack and put it into RDI so that we can do the exit syscall. So let's push this onto the stack. So we'll do output, and we need to do well, I guess first we need to put the value into a register, and then we can push it onto the stack. So we'll just use racks, and we'll just say everything's 64-bit for now. We're not dealing with types. We'll just say everything's a 64-bit integer for simplicity. So we'll move into racks the expression integer literal dot value. That's quite funny to look at. And then we can give it a new line. Okay, and then, but we don't have output. That's a problem. Maybe when we construct this, we pass in the generator. We pass in like a pointer to it. I think this is going to make some people cringe. I think this is going to make some people cringe. And when we do this, we can pass in this. And then do gen like that. And then we can do gen dot m output. Oh, you know what? No. We can't do that. We don't even have an output here, I just realized. So maybe output needs to be, I think output needs to be a member. So let's create a string. And then we'll make it an output. And then we'll use that instead of this output, so that we can access it like anywhere inside of this class. But why can't we stream into it? Oh no, what happened? Invalid. Did you mean m input? Maybe because there's errors up here I need to take care of first. Because this can no longer be const then. I see. Okay, and then when we get here, we can pass in, actually, so we can pass in maybe output. And then in here we have a string. And then we make this output like this. No, let's pass in the generator. Let's pass in the whole generator so we can access anything in here. And then I'll pass in this to it. And then we can do gen.m output like that. So this is like where we are capturing this in here. We'll lose const qualifier. Well, this is no longer const then. Okay. Yeah. That'll work. The beauty of C++ is really coming out here. This is modern C++. This is the best way to do it for sure. Okay, this can be made const. Really? I guess it can. Okay, so we have gen m output. Okay, so we move it in there, and now we want to push it onto the stack. So m output, and then we will do push, and we want to push from racks. Okay. And now it's on the top of the stack. Okay, so that should do it for this. And now, and what do we have here? It must be marked explicit. Okay, fine. Now, what we can do is, you know what? Since this is a struct, can I just do .gen equals this? There we go. That's much simpler. There we go. There we go. Okay, so if we get an identifier, we got to do something special. So we'll get to that in a little bit, but let's get everything else working. So we have a statement exit, and so we need to, if we have a statement exit, we need to generate the expression inside of the exit first, right? If I go to here, exit has an expression in it. If we generate the code for the expression, then that means that the value of the expression will have been pushed onto the top of the stack. And then when we do the rest of the exit here for code generation, we can then pop it off the top of the stack and put it into RDI. Okay, because whenever we generate an expression, we'll make sure that we push the value of the expression onto the top of the stack, just like we did here, and we'll do the same thing for the identifier for the variable when we get to it. So we will we need to do that first. So we can do gen expression statement exit dot expression. We need gen in here. So generator gen. We'll make this a pointer, and then we will do gen equals this. And by the way, guys, raw pointers are fine if you know the lifetimes of them. Okay, like don't be afraid. It's okay. It's okay. I know you might feel a little dirty, but that's okay. It's fine. You will live. Look, I'm not gonna write in Rust just so I can wrap myself in bubble wrap to output assembly. Like, come on. Okay, we can handle some raw pointers. So we'll generate the expression, but we need to do gen expression, just like that. Is the return value of the function is not used. You know what? We're no longer returning a string from any of these because we're just streaming directly into the output. So this can actually just be void. Now we don't need it, so we can actually get rid of this no discard. So, and this is the same is going to apply for this because we have a global output member that we're just streaming into. So we will remove that. Okay, so we generate the expression. So now the value of the expression is at the top of the stack. And now after we move 60 into racks, we can go ahead and, after I put gen here to silence this, we can pop from the stack into RDI. So gen m output, and we will pop off the stack into RDI. And then we can do the syscall. And that should do it. We can make that const. Okay, and the reason why we can make this const is because this this pointer isn't being changed, even though like the thing it's pointing to is changing. The pointer itself is not being changed, so this can be marked const. I think we can actually mark this as const. Can we mark this as const? Yeah. Oh, but now it doesn't work. Yeah, so we can't do that. All right, we can't do that. Okay, so we have one more problem here. What is this problem? So gen statement will automatically stream into the output itself, so we don't need to get that anymore. So we have this, and I think where we are at this point is that we should be able to do exit 7, and it should still work even though we substantially changed everything. Oh no, we have lots of problems. Oh, because we didn't fix our main CPP file after changing everything. So instead of parser.parse, it should be parser.parse program. And then we should get a node program instead. We'll do program. And if it doesn't have a value, we'll just do invalid program. And then we create a generator, and we need to pass it our program. And then we can do generator.generate program. And what is the problem here? No matching constructor. Really? Node program. Huh. Oh, because we need to call .value on it because it's an optional. Okay, now we should be okay. Ooh, what do we have here? What do we have here? Ah, we don't return. So we need to return our program. Okay. Okay, so does this actually work? 7. Okay, so even though we made all those changes, so that means we actually, so if we look at the assembly, this should be quite a bit different now. It'll be less efficient, but it'll work. Okay, the indenting is screwed up. So move and push. Why did I forget to indent something? Move and push. I did. We will indent it correctly. We'll run it. Okay, so in our start here, so we take the 7, we evaluate the expression, which in this case is just an integer literal. And so we're going to move 7 into racks, and then we're going to push that 7 from racks onto the top of the stack. And then, so that's the expression that was just evaluated. Then we move 60 into racks for the exit syscall. So now this is we're in the parsing for the exit statement. And then we pop whatever was that was evaluated from the expression into RDI, which in this case is 7. And then we perform the syscall, and it'll exit. And if we don't exit explicitly, well, then it will just exit with 0. So if I don't have anything here, if I just do nothing, and I run it, it should no longer say invalid executable as it would before, but instead it just exits with 0. So that's a valid program then. Okay, so that's all working correctly. So then we actually have to get to the variables part, which is the more interesting part. So how are we going to do that? So the thing with variables is that we can push them onto the stack. However, what about this scenario? If we do let x equals 7, and then we do let y equals 8, and then we exit with x, let's think about how this would work. If we push 7 onto the stack, and then we push 8 onto the stack, we can't simply pop whatever's on the top of the stack and then put it into exit, because 8 is on the top. So 7 will actually be underneath 8 on our stack here. So if I were to visualize this, we'd have 7, we'd have 8. So we start off with our 7, we put it onto the stack, and then we put our 8 here, and then we go ahead and do our exit. We can't simply pop off the top because 7 could be under 20 variables. I mean, we might have like a whole bunch of different variable declarations. So what we actually need to do is keep track of where 7 is located in the stack, or where, I guess, x is located in the stack. And so what we can do is we can say, okay, we're at like the 0th position on the stack. So the value of x would be in like the 0th position, and then the value of 8 is in the 1st position. And then what we can do is, since we have a stack pointer in a register during runtime, we can simply take the offset of where the current stack pointer is, focus, Focus, yo. Webcam, hello. What is happening? I'm blurry. Let's see if it'll clear up. But we can take an offset from that and then reach into this underneath the stack and read the value. Remember, we can't pop it off the stack, but we can at least read from it, which is all we need to do in order to actually use the variable. So instead what we can do is, because we want to push the value of the value here onto the stack, what we can do is read from this value on the stack. We can create a new value, which is a copy of this, push it onto the stack, and then when we go to our exit, it can now pop it off the stack. So essentially we're taking a copy of x, the value of x, and pushing it onto the top of the stack so that when we call exit, we can now get that value. Okay, so in order to do that, for each variable, we have to keep track of where it is on the stack. And because of that, during our code generation, we actually have to keep track of where the stack pointer will be at runtime, but we have to keep track of that at compile time. So that means we're going to have like our own kind of stack pointer at compile time that we can move around. So we can make it a size t. We could do m stack location. All right, we'll just do m stack location. And that will just be starting at 0. Okay, and so it starts at 0, and now we actually need to keep track of any time we push or pop. Now the thing is we pushed and popped over here, but it wasn't a variable. But it doesn't matter, because it doesn't matter if we have a variable or we have some other a literal that we push on there. We still have to keep track of it. So that means we're actually going to have to abstract away these pops and pushes into their own methods so that we can keep track of our stack location. So in here, we will do a void push, and we'll take in the register. So we'll take in a string for the register, and we will go m output, and we will do the push for the specific register. So we'll do the push for it, the caller actually, for the caller, and then we will do m stack location plus plus. So we add one to the stack. So we know that, okay, we added one. So maybe instead of location, it's like the stack size actually, because we're just keeping track of how many there are. And we'll just say that a 64-bit integer is a size of 1, because we're not gonna deal with anything smaller than that for now. In the future, we can use bytes for the size, but we'll just do full. We'll just do a 64 bits as a single unit, because that's the smallest piece we're working with. And then we can do void pop. We will take in a string and the register. We will perform the pop for the caller. Pop. And then we will do m stack size minus minus. So now we know how big the stack is at all times, as long as we use these two methods. So anytime we do push or pop, we need to actually use it. So in here, instead of doing push racks, we can do gen push and then racks, just like that. And then anywhere we use pop, we need to make sure that we use our methods here. So we will do gen we will do pop, right? Pop into RDI, just like that. All right. So now we are able to keep track of the stack size. And this isn't modifying the output assembly at all. This is just for our own bookkeeping. So now we need a way to keep track of what variables have been declared, because now we're doing variables. We can't just, we need to make sure that we don't do something like this. You can't declare a variable twice. So we need to keep track of what variables we have. And that sounds like something we can use a map for, an unordered map. A hash map, as some people would like to call it. So, but in C++, we call it an unordered map. So, and that's just key value pairs, and we'll make it, so we'll do an unordered map. I'm guessing we'll have to import this. And then we'll have a var. We'll have a struct that's a var. We'll do vars for variables. So we'll go ahead and include that. And then we'll create a struct for a variable. And in the variable, we're going to need to know its position in the stack. So we'll do stack location, and this will be size t. Just like that. We might actually not need any more information at this point, but we'll probably want some more information in the future, like its type. You know, I would like this to be statically typed, so we'll include like a type in the future for now, but we'll leave it here. And we will just default that as empty. And so now when we encounter a let statement, we need to first check to make sure that there isn't already a variable declared with that name. So that's a simple check of just doing gen m vars dot contains. So if it contains statement let dot identifier dot value dot value. So if it contains it, that's bad. We need to do we need to get output an error. So identifier already used, and we will print out the identifier so that they know. So statement let identifier value do an end line, and then we will go ahead and exit with failure. Okay, so now at this point we know that the variable is unused, so we can go ahead and include it. We can go ahead and insert it into our unordered map. But first we can push it onto the stack, or we want to get the location of it. So maybe we want to, let's insert it first into our map. So we'll do gen m vars dot insert, and we want to give it a pair of the name. So this again, value, and then the stack location. So we need a var, and then the stack location will be just the size of the stack right now. And this is going to be from gen. Okay. So now we inserted it into our map. Now we can actually push it onto the stack. So we can do gen dot push, and we can push the, actually let's take a look here. Oh, it's an expression. Ah, that's even more interesting. So that means that we have to actually evaluate the expression. So yeah, because you can assign it to another variable. Yeah, I didn't think about that. So you can actually do something like let x equals, well, if we do this correctly, let y equals x too, of course. So we need to evaluate the expression. So before we do this, we need to do gen expression statement let dot expression, just like that. So now the value of that expression is now at the top of the stack. Okay, so if we were to do this, then that means that when we're generating this line, when we're generating the second line, it will evaluate x, which we haven't written the code for that yet, but we will. And then it will take the value of x, which is 7, and take a copy of it because it's further into the stack, and then put a copy of it on the top of the stack. And then we're going to assign it in our map of variables that location is now the y variable. So we're giving it a name. Okay, so in our generation, we generate the expression, we can insert it here, and then you know, I feel like this is going to be an off by one thing. I think I need to do this first, because I want the pointer where it starts. I want the location to be where it starts. This might go after or before, I don't know. that's a thing that we can just, it's a 50-50 chance. I don't feel like thinking too hard about which one it is until we just debug it when it doesn't work. So we will generate our expression. And now we want to push that onto the stack. No, it's already on the stack. So then we're done then, over here. It's on the top of the stack and we insert it. Okay, so this is it for the variable generation. I think that should do it. We put it onto the stack because the gen expression will put it on the stack for us, and then we just assign it, we put it in the map. All right. And this is the last part we need to do, which is if we need to use the variable, essentially. So in this scenario or in this scenario, that's where this is going to be called. That's where this is going to be called. So this is where we extract out the value of the variable, and we need to put a copy of it onto the top of the stack. So how can we do that? So we have an expression identifier. First of all, we need to make sure that the variable is declared, because if we do something like this and put exit z, we don't have a z. So we need to first check that it's even there. So in order to do that, we will say if, I think maybe we could do a find. If we do gen vars.find. Yeah, but what does find return? Because what I want to do is, let's see, if I do find like this, and I give it a lambda, and each one, we'll just do auto, I can't remember what this is, so thing. I can't remember the type of this. So if, what is thing? Thing dot, it doesn't even know. What is the issue here? Does it need to be constant? Something is not working right. Okay, you know what? We'll just do this the slow way. I know this is inefficient, but I'll do this correctly later. If not expression, if not gen m vars dot contains expression ident dot value. So if it doesn't contain it, then we return an error. See error, invalid identifier or undeclared identifier. And then we will give it, print it out just so that they can know which one we're talking about. And then we will exit with exit failure. So now we know that it contains it. So we need to get the value of it. So in order to get the value of it, and then we want to take the value of it and put it in, we need to push it onto the stack. So we're getting a value from further down onto the stack, taking a value from further down on the stack, make a copy, putting it on the top so that it can be used. And that means we need to take an offset from where the current stack pointer is. So the current stack pointer is here. It's here. Here's the stack pointer. And then we say it's at location, we know X is at location 0. So that means that because we're at a size of 2, we need to do we need to offset the stack pointer by 2, take a copy of this, and then push it back on the top, like that. So in order to do that, we need to get an offset from a stack pointer, and I can't remember how to do that off the top of my head, so we are going to Google it again. So we want to do offset from stack pointer x86-64 assembly. Let's see what we get using a frame pointer. Okay, this isn't what I want. Maybe you know what? I think I'm going to specify NASM. Maybe, what is it? NASM stack pointer. I can't remember what register it's in. What is, so it's something like this. Yeah. Declaring pointer. I want... there's a register for the stack pointer. x86-64 stack pointer register. I think I just don't know what register it is. So it's RSP. Okay, so that's what it is. RSP. So it's the stack pointer. So I think maybe something like this. So we can do gen. I don't know if we need to move it into a register before we can push it onto the stack, but maybe what we can do is we can push onto the stack what we have from RSP, the RSP register, plus the offset. So we can do a bit of string concatenation here. So plus the offset of a, we have the stack size minus the mvars.at gen mvars.at here. And I think, you know what, I'm going to make that into its own variable. We'll do like the variable const auto var equals gen mvars.at this. So we'll just keep it as a reference. It doesn't like this. Unmatched. Did I add an extra? I added an extra parenthesis. Okay, so we have, so we're getting the offset into the stack. And we have a problem because I think what we want to do is this. Oh, and var dot stack location. And then we want to add that. But it doesn't like that. Am I gonna have to use a stream for this? Or you know what? We can use string formatting, I guess. Let's just do a quick string stream. We'll just call it offset. And we'll do offset. We don't care about making things fast right now or memory efficient or anything like that because we just want things to work. Otherwise, it is just premature optimization, of course. So I'll put an offset in here, and I forgot a semicolon. And then we need to do string. I'm not 100% sure that that's the correct syntax of doing that, but let's find out. Let's find out. And I'm sure some of the math in here is a little bit off anyway. But let's just try it and see what happens. Undeclared. Oh, so our error message already works, so that's pretty cool. So what do we get if we do this? Operation size not specified. Okay, so this is an error from not our program, but from the assembler. So operation size not specified. Okay, I think it's coming back to me. I think with NASM, and I'm not sure if this is an assembly thing for x86 or this is just a NASM thing, but I think when you push using some kind of offset like this, we need to specify the size of the data that we're pushing if it's not from a register. And because we're using 64 bits, I believe that's denoted as keyword, as quad word, as a word is 16 bits. I think a word 16 bits. So a quad word would be 4 of them. I might be wrong on that, but I don't care enough to Google it. So let's go ahead and see if that did it. Okay, so let's see if that works now. We get 0, which is not what x is equal to. And I think I already realized something, is that this offset is in bytes, and our stack location and stack size is using 1 for 64 bits. So we actually need to multiply this by 4. So let's see if that works. Oh my god. Okay, I wasn't expecting that to just work. Okay, so sanity check. Let's do an 8 here. Let's just do that. Make sure that this is functioning. It's still 7. And so if I now do Y, do we get an 8? Ah, we don't. I knew it was too good to be true. We almost got it, though. We almost got it. So, what exactly is the problem here? I'm not really sure. Why do we get 0? Well, actually, we can just take a look at our assembly. Okay, first of all, I forgot to do proper formatting again. So we need to do, where's our assembly? Oh, it's under the push and pop that I created here. 1, 2, 3, 4, 1, 2, 3, 4. So now we can actually look at our assembly correctly. Okay, so what is the problem? So we move racks into 7, or 7 into racks. So maybe we can visualize what's going on here. We won't visualize the registers. We'll just keep it in our minds and hope that's enough. So this will be our stack. So we move 7 into racks, and we push racks onto the stack. So our stack is now here. Our stack pointer is at the top of the stack. We then move 8 into racks. So we have 8 in racks. And then we push racks. So now 8 is up there. We then push keyword of RSP plus 4, which should just be here, which should be the 8. So we should be just taking a copy of 8 and pushing it onto the stack. But it's not. It's not. Why is it not? We get 0 instead. I have a feeling we're off by 1. I have a feeling we're off by 1, and instead of thinking too hard about it and wasting brain power, what we can do instead is just find where our offset is and just subtract 1 and see if that does it. 8! A! So it looks like we were off by 1. Okay, so I see. So in order to get 8, we actually just keep the stack pointer where it is. And then if we want to get 7, we then move it here. And then when it's here, then we take 7. Okay, so it was just an off by 1 thing. So now if we go ahead and put X in here, we should get a 7. No! No! Oh, that's so unfortunate. Oh, no. No. Maybe it's minus. Maybe it's not plus. Maybe it's minus. Maybe we need to subtract from the stack pointer. I gotta be honest, I can't remember, so this is all just trial and error. Because that's not working. What if I put Y? We get 8. Which is right. Okay, I think, so the stack grows from the top, if you don't know. So if you look at a executable memory layout, what you'll see is that you have here, you have the stack, and the stack grows down. And so this is a low address. So in order to, so our stack in draw.io here is kind of upside down, or this one's upside down that way. So what we need to do is, in order to go back into the stack, we actually have to add to it. So it was addition. So addition is the correct thing to do. We do need to add to it. Is it 4? Wait, no, 4. Wait, no, I think it's 8. It needs to be 8. Right? Hold on a second. 8 bytes. Right? Yeah, I think it needs to be 8 bytes. Yes, it's 8 bytes because there's 4 bytes in 32 bits. There's 8 bytes in 64 bits. So we weren't offsetting far enough. All right. So now if we look here, okay. So we have this program. X equals 7, Y equals 8. We then exit with X. So if we think about what's happening here, we have 7. It's in racks. We push it onto the stack. So our stack pointer goes from here to here. Now we create 8 in racks, and we push it onto the stack. And then we move the stack pointer up. We now want to use 7. So we want to push what's 8 bytes further back into the stack, which is here, which is our 7. And we want to push that on the top of the stack. So essentially we make a copy of it, put it on the top of the stack, here, and then we move 60 into racks for our exit, and then we pop off whatever is at the top of the stack, which is a copy of X, and we put that into, well, we pop it, so that means we take it out, and put it into RDI, and that's what gets exited. So the reason why we do a copy, I mean, it's kind of like how C works or C++ works, or I guess Rust does this too, even though it's moved by default, is that because it's such a small type, it's a trivial type, which means it's just copy by default, right? So we're essentially copying X into this function call here, okay? I guess if it was like a heavier class that was like really big and took up a lot of space, you probably wouldn't want to like copy and paste it here. You'd probably just want to like either move the entire value, or you want to pass in a reference to it. But for trivial types, like just a 64-bit integer, it's just easier just to copy and paste it in there. Now, of course, some optimizations that could be made would be like, okay, well, we're not using X anymore in this program. And so maybe we can look and see, okay, X isn't being used anywhere, so we could just use X here, or X isn't being modified here. We're just reading from it, so there's no reason to copy it. We can just pass in the location of it onto the location of it on the stack. So there are huge amounts of optimizations we could do, but we're not going to be doing optimizations yet. We're just doing things simple. So I think that took care of everything. It's a bit of a long one today and a bit of a confusing one. I highly recommend that you take a look at the code if you're interested and really think about what's going on. I know some of maybe the programming patterns aren't super great in here. I gotta be honest, there's a reason why I didn't call this a tutorial or like how to write a compiler. This is, I'm writing a compiler and you can watch me stumble around and maybe you can find that useful. So I realize that some of the things I'm doing won't be 100% perfect. And by the way, guys, I know some of the things I'm doing are slow in terms of performance. It's okay. It's okay. Really, we're okay. Our language is very simple, all right? Look, just because I use 2 end lines here, meaning I do 2 write syscalls to standard out, doesn't mean that my compiler is bloated, okay? Relax. It's okay. This looks prettier than having it all on one line with like a new line on it, okay? There's some things you need to worry about, some things don't need to worry about, okay? So I think that'll be it for today. I hope you guys enjoyed. Next time, I think we can actually start to do math, right? So we could do something like 7 plus 5. That'll be interesting, because then we can get into like operator precedence and all that fun stuff, and really make our AST even more complicated, where we might have even like nested expressions, something like this. Ooh, 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 spicy. We're gonna be spicy next episode. But thanks for watching. I'll see you guys next time.